All right, let's get started here in the room. I know we've got some people online as well, so welcome. This is going to be a busy week or two for Tide. We have our workshop on Wednesday, and we have a lot of visitors here this week and into next week, so we have a number of seminars that'll be on. We were very lucky to have Ralf Peek here for the last nearly 6 weeks now. It's been over 5 weeks, I think. It was fortunate that the timing worked out that you were down here for a project. Ralf been here and visited us before as part of Tide and gave a seminar before in the city. So we've really just grabbed the opportunity to have Ralf around and working with us and the Tide team for now for, as I say, over 5 weeks, particularly with our Theme 3 team looking at spanning of subsea pipelines. And that's really going to be the topic of today's talk as well. So we're tracking for questions online. So Ralf will give a presentation. If there are questions from those who are joining online, please send them through, and Mariam's checking those, and we'll pass those on to Ralf at the end for any questions. Otherwise, for people in the room, please save up the questions and ask them at the end, and we have a good session. So, Ralf, if you'd like to come and join us. So, Ralf Peek is, well, in pipeline space, a guru, a bit of a legend in this space from his many years working on topics related to subsea pipelines. We've certainly benefited from your experience, Ralf, over the last couple of years in your involvement in Tide, and we're looking forward to that continuing into the future as well. You gave a talk before, I think in Woodside Building about a year ago, on spanning pipelines and vibrations. I guess you'll build and extend on that a little bit today. We do have, as I say, a lot of people online as well as in the room. So without further ado, I'll hand over to you to talk to us about subsea pipelines. So, thanks, Ralf.
Thank you very much for such a kind introduction. Certainly, it's fun to be here. Lots going on, and I've always enjoyed coming here. And so also very pleased to say a little bit about what I've been doing, mainly in my spare time, because I'm not allowed to talk about the things you do for consulting, right? So spans with nonlinearity. Okay, let's go. Why spans? Well, I guess when I left Shell in 2016, I thought I was going to be without a job because the oil price was way down and so on. But scour continues to happen, right? And spans continue to form, and sometimes these things raise questions. So I found there was work to do in spans, and once I got involved, I started saying, well, there's a huge amount of work done on spans, but yet when we come to make engineering decisions, there's still quite a lot of uncertainty. And what are the key points where with relatively little effort we can get something, because I'm not a researcher 100%, I'm more of a consultant, but where are there things that with little effort that I can do myself or within the team, that here, if now I'm trying to extend, to happy to be involved in these things here, make an impact. And then also, as I go, improve tools that you could then use. So the intent is more or less to get tools that you can improve in the actual consulting work. Very good. Now, how about nonlinearity? Why do we talk about nonlinearity? What is there about nonlinearity? I mean, it's easy to do nonlinearity. Any computer program can analyze nonlinearity, but it needs to do so in a time incremental way, in a time domain. And in reality, if you take any code that can do that, and everybody would say you include the nonlinearity, but the standard analysis methods for spans say that you then need to do a modal analysis. The moment you press this button on your computer that says modal analysis, you are saying that for the dynamic response, at least for the part of the increment in response beyond what I call a reference static equilibrium configuration about which the vibrations occur, for that part, it's linear. It's easy to get rid of that assumption, but it hasn't been done. Why hasn't it been done? Well, the reason that hasn't been done is because there is the VIV involved, right? And the VIV is difficult to formulate in the time domain. It's difficult to formulate in the time domain. And So what people have done is what is mostly done, and that's the practice, is use the response functions that are used for this. And this gives you the amplitude of a single degree of freedom system as a function of the current velocity expressed in pipe diameters per natural period of oscillation and the damping. And this then forms the basis of all the assessments, almost all the assessments that I'm aware of that are done in pipelines. Right? There are several parameters here that are not implicit, that DNV says they're implicit. That means that they have thought about them, but the guidance they give do not include them. Right? That I list there: mass ratio, Reynolds number, roughness, seabed proximity, turbulence. Turbulence is being addressed in tide, I understand. And they are known to influence VIV, but not included. And presumably DNV have done a lot of work to come up with this thing, have considered all these things and think that for the things that we have for pipeline, this is reasonable and conservative. Now, unfortunately, there's very little documentation of why it should be this. Right? I have sat in JIP meetings that come up with some of these things, and often there's a lot of interesting discussion. But then even while still at Shell, if I still asked, well, where's the report that justifies all this? They say, actually, there's a few papers out there. But the papers are not giving you enough information to justify this. Right? But it's accepted. It's accepted and it's widely used. So if anything you build on this will be accepted. So that's okay. So what are the ways to deal with nonlinearity? I've already referred to the time domain methods. If you do a CFD calculation, that's a highly nonlinear calculation and a highly complex calculation because it's 3D and you have to resolve the turbulence. You have to make certain assumptions about turbulence that is at a scale that you cannot resolve in your grid. So you have to make approximations there. And but then adding a nonlinearity, when I talk about nonlinearity, I refer to basically nonlinearity of the structure or of the soil. That is not of the water will always be nonlinear because it has, yeah. So the incremental complexity of making your structure nonlinear in a CFD calculation would not be large. It's a small increment. Most of the computational effort goes for the CFD. Right? So that can be done. That's one way that can be done. But it's very compute intensive, and I think there's still not that much. There's a lot of validation, but whether if you apply it for one case that you are interested in, you ask the question, has there been the relevant validation of this model? Then that's sometimes a difficult consideration. And then the more simpler, more efficient things are like a wake oscillator. For instance, wake oscillator, there's a lot of papers on wake oscillators. And you say, well, if you have a pipe with current coming there, the blue arrow means current, then the current gives you VIV and it gives you forces. And those forces you can represent approximately by attaching a mass to it with a spring and a damper, a linear spring and a damper that has, a nonlinear damper that has basically has negative damping up to a certain amplitude, which gives you the VIV excitation. And beyond that, it goes into positive damping. Right? So there have been papers tuning this and so on, and mostly, many of them just look at 2 degrees of freedom system, but you can easily extend this system to complicated nonlinear things. You just add, you can easily add a mass to each node of your finite element model and do this type of analysis. But of course, you have to validate it for that as well. What has been a lot of work done recently also in Norway that started with the work by Mats Thorsen that is also looking at another time domain VIV model where you can do that. And they're trying to validate this and so on. But none of these have seen a lot of use in practice yet. I think there's potential, and if you have a really nasty nonlinear problem, I can't think of another way. I can't think of another way. So I think it's a good one to have in your toolbox. And if you need to use it, use this together with other things and try to come to some judgment of what might be the But for here, I'm focusing on the methods based on frequency domain and based on the response functions that I just showed earlier. There are other frequency domain methods that work. That's basically Vivana and Viva and to some extent Shear 7, that is based on also response functions more locally for a single section. And the assumption is that it moves harmonically, and then you look whether the flow injects energy or takes energy out of the flow in those models. Okay, so here, and then here's the thing about the nonlinearity. What happens to if you do it in the frequency domain, and generally you will linearize, and I'm trying now to improve on that, and still I need to linearize, but I use a linearization that may be amplitude dependent. For instance, here, if you have normally what a finite element code would do is to if you don't say anything and you say, I want modal analysis, it will use the tangent stiffness at your last increment, and it will use that to do the modal analysis. If your last increment had, say, lateral displacement of a lateral buckle, for instance, then the tangent stiffness might be 0 where it had been slipping. Or if it's an unloading stiffness, it would be high, And that's for that reason, people often replace it by some other stiffness based on engineering judgment. It's a dynamic stiffness that might be different from the static stiffness. Right? But if you now want to include nonlinearity, and you say, well, actually, here what we use is secant stiffness, and the secant stiffness will depend on the amplitude, because if I increase the amplitude, the secant stiffness will tend to become lower. Very good. So let me now tell you where is the evidence for nonlinearity. I mean, it's been known long ago that nonlinearity in span is important, but still the practice is not doing much about it. But here's our evidence that we collected with the help of UWA for these spans, and that means this comes from a plug test that we did on an operating pipeline. And this slide here shows you the accelerometer. That was, I think, Conlon McLaughlin was very much involved in making this. And it was then attached with this clamp to the pipeline. And then what we would do is we would pull the pipeline with a weak rope, so that the rope had a capacity of 600 kilos, so 0.6 tons. So, and then it would break, and then the pipeline would sort of oscillate. And unfortunately, the ropes that we used, they didn't break very clean, so they broke, and then you lost some of the energy that you might get otherwise. And this part of the clean breaking gave you a not very clean signal, but still you got some amplitude. This is a typical acceleration trace. There's this thing. Oh no, I'm covering with my finger perhaps. Ah, yeah, there. You see in the beginning, I think this is probably the first very little bit. That's probably the breaking of the rope, and maybe strand breaks. And then here you see some higher modes. And then later on, it seems to settle more into the first mode that we are trying to investigate. Now, how do I try to get information out of this? Well, I mean, the most obvious thing is you say, pick the solution for a single degree of freedom oscillator and see if it fits. Well, it doesn't fit very well. If you try to fit the beginning, it doesn't fit at the end. And if you try to fit the end, it doesn't fit the beginning. Right? So this is interesting. So what did I do is I divided it into several segments, each segment of 2 periods. And then I say, I'm going to pick a model in which it's a single degree of freedom oscillator, but the properties, the natural period and damping ratio, may change from one phase to the other. And there are certain continuity conditions that you must satisfy. And now you have a model that has several parameters, and you can adjust the parameters to get an optimal fit. Because I really wanted to get the best out of that data. You could just have counted and kind of eyeballed it, but I wanted to really get the best out of these data. And so that's what we did. And then for every, it's really as a function of time we have the properties, but then we also have as a function of time the amplitude is decreasing. So then I plot those properties as a function of amplitude, right? And I can do that for not only one test, but several tests on the same plot. Okay. So this is what that looked like for a 28-meter span, and it's one that had soil on both sides. Some spans had like grout bag supports or other things. No, this one had soil on both sides. And here is the results. What you can see is although the amplitude that was achieved was small, 4 millimeters is 0.006 of a pipe diameter at the end of this plot. You can see here our natural frequency, for instance, that it goes down from about 1.8 something to 1.6 something, maybe a 15% reduction. Now, a 15% reduction means a 30% reduction in actual stiffness, if you were, right? Which is quite a lot, right? Significant for this small amplitude, right? So it's significant nonlinearity. The damping also, it goes up quite a lot, right? Because I think it's, and the only reasonable way I can think of explaining this is that it came from the soil resistances at the end. And luckily here, Vasileios here for Tide is doing a lot of, is doing centrifuge tests to get better pipe-soil interaction models of this soil resistance and looking at doing some of these calculations for that. So that'll be quite interesting to see what comes out of that. So yeah. So that's why we had the nonlinearity is important. How do I analyze this? I've talked about this the previous time. Now there's a few complications that the problem is a bit more complicated but in principle it's the same. In this case we have a static equilibrium configuration, which I call the reference, the RSEC, reference static equilibrium, and a dynamic increment. And if you look at the equation you would have, the modal equation, you have basically a stiffness that now depends on your solution, So instead of getting in the modal equation, if you get one amplitude, it's good for all. So here it's going to be amplitude dependent, what the solution is. And if you just look at that problem, it just looks like this one, which is basically like a structural bifurcation problem, just like a buckling problem. You have a principal solution branch, and at some point your tangent stiffness becomes singular, and then there will be bifurcated solution branches here. And so many, many years ago, when I was at university, before I came to Shell, I was doing a lot of work on these type of problems. So this one is relatively easy, right? Compared to sometimes with structures that buckle, that have many simultaneous models, it can be very complex, the picture that you get around the bifurcation points. So I could solve this with the finite element program VIV. And there are some, compared to, I think some years ago, I talked about a problem also involving this, and was just an inline response of a single span. And there are a number of things that are different now. One is that I have dynamic as well as static. I have a static as well as a dynamic displacement, whereas in the past I had just only dynamic displacement. Then there can be asymmetry in the dynamic response, in the sense that if your force deflection relationship is not exactly antisymmetric, then going in one direction or going on the other direction will have a different response. Like, for instance, in cross flow, if it's going up or down. If it goes down, it has soil resistance. If it goes up, it has no resistance. Right? And then, of course, I have dynamic response in all three coordinates, and I've also now included geometric nonlinearity in the span itself. The moment you have large rotations, let's say, and you keep the axial restraint, you get geometric nonlinearities in the span itself. So those could just be included. For the asymmetries, before I would just track the bifurcated branches in one direction, because the other direction will be the same. But since it's asymmetric, I've tracked both directions to see if it makes any difference. Okay. So then what would be a good problem to apply this to? Phil had been telling me, oh, we got all these, you're guilty. You know, there's a lot of CRB spans here, and you are part of to blame for that. And they have scour, right? Problems, right? Scour problems, and they're getting longer, and then people are concerned about these. So I thought this would be a good example to apply these things to, and the European spans, and what they are is this. I came up with this again. I think that the need is what mostly creates invention, because it's not just of having the idea for it, but also there must be a need for it that project managers are willing to take the risk to do something new. If the old thing can work, it's unlikely they will, because they want something very, very reliable. You know, if you're a project manager, then anything that goes wrong and delays your project is trouble, right? So you don't look for really high optimal. You look for something that you know that can be done, and it has been done, and it can be done in some given amount of time. But in this case, we had kind of, there were reasons that we wanted to get the stresses quite low. There was challenges with the welding, getting the CRA welding to go. So then came up with a proposal to do this, so you could get buckles that are trigger buckles quite closely spaced, and without any risks that one fails to trigger, and then you get more displacement in another, right? And so that's when we started doing the ZRP spans in the South China Sea. And well, this slide shows you how it works. You put in this strange thing with a post on the seabed, and then, so I've sketched it here. Oh, sorry. And then basically, you lay the pipeline in a straight line over this thing, and typically you aim for some distance away from the post, a landing point, a little bit distant away from the post. The sleeper that goes horizontal is normal to the pipeline direction, and then once it's firmly seated on that, and in the analysis I did that so that there'll be a zero slope on the other side. The slope on the it becomes zero. Then the lay barge moves laterally. So then once it's firmly seated, then you move laterally maybe by 5 to 10 degrees, which is quite a lay barge movement that you do all at once, right? Because normally a lay barge will only move at a certain angle of the direction of the pipe, because the angle determines the radius of curvature that you're laying. Now here you're putting perpendicular, so in theory you're moving as if you do an infinite high curvature or zero radius of curvature. That's why I call it zero radius band. Right? And so that's what the CRB is, and there's been quite a lot of people using it. I think a lot of these things. Yeah, I don't know. Sometimes I feel that these things come out as new things, but then they start being used so much that it's not always clear whether they're used where they're necessary. Yeah, maybe they're used more than necessary. I don't know. But this is now a little bit more detailed here, and it shows the post as laid, it buckles, and it moves out. And it gives you I give you some details of the modeling. I made now very simple modeling assumptions for this, for the pipe-soil interaction and the pipe support interaction. I just assume these are all fairly rigid frictional surfaces, so that it reaches the friction coefficient, it just slips at a constant force. No static and dynamic friction difference, just reaches a constant force and it slips. That is the assumption made, right, here. Now with Vasileo's work, we will be able to improve on that for the inline directions and things, but for now, for illustrative purposes, it's just this slip, and it gives you the friction coefficients there. On the sleeper, I took 0.5. Some people say that, I've heard that, I don't know whether Fraser told me that on On the sleepers, sometimes they try to make them low friction. They might be lower friction than that. But normally, say, steel to pipe, this is not unreasonable, I don't know. Okay. So this is the analysis done. And that is the sketch, and these are now the results of analysis. For the analysis, you need to first do the static part, quasi-static part, which is basically simulating the pipe lay. So it's just all simulated. You simulate the lay barge, lay, the S-laid, and then I simulated 2 operating cycles because the configuration changes a bit with the buckles. The buckles become wider. And I simulated 2 operating cycles, and I said, well, after 2 operating cycles, let's look at what the VIV response is. So that's what we're going to look at now. And so basically apply this amplitude-dependent mode type methodology, and here comes the results. It shows the modal damping ratio and the inline and cross flow. The modal damping ratio I only showed for the inline, but the frequencies I show for both inline and cross flow. Now, normally when you have a span, the span kind of sags like this, and then the cross flow frequency tends to be a little bit higher than the inline frequency, because this sag of a span gives you kind of, it's like an inverted arch. It gives you a bit more stiffness. But in this case, it's the opposite. Our inline natural frequency is higher than the cross-flow natural frequency. Well, why? This is basically because of the ZRB nature of this thing. We have a lateral outer straightness, and that acts as an arch. And I'll show you here how it acts as an arch. Here is in green is this is I've sketched it. There's also results. In green is the pipeline before deformation, and in red I showed what the mode shape looks like. And there's one side where the pipeline is moving outwards, it's pulling length into it, and where it's moving inwards, it wants to go into more compression. So as a result of these movements here, at the support of the ZRB support, where I put this red arrow, it will tend to want to move axially. So it's going to make a difference whether that slips or does not slip. Right? And initially, at very low amplitude, it does not slip. So that's why, oh, no, I jumped the slide. That's why initially you have basically no damping, and initially the inline frequency is constant. When it's not slipping, it's elastic. But the moment it starts slipping, the inline frequency starts dropping, and the damping starts going up, right? Because you get a lot of energy dissipation from this thing. And what you can also see here is that at about A over D 0.15, the 2 modes become coincident in natural frequency, and then strange things can happen when they become coincident in natural frequency, as we will see. Right? And okay, so now this is the effect of the axial displacements, why that's so important. And here are, what I've done here is plot the mode shapes, the modes are both in sort of like a mode 2 of a soil to soil, a normal span. But what I've done here is plot the modal displacement at a node somewhere mid-span. Okay? Somewhere mid-span, and I've plotted the horizontal and the vertical mode. And what you can see is the vertical mode remains pretty much vertical. It's vertical. The horizontal at first has only a very small vertical component, but as the amplitudes of the horizontal moment get larger and the frequency starts approaching the frequency of the vertical mode, suddenly that mode shape is starting to veer off and have a larger and larger vertical component. Right? So what happens there is complicated, let's say. But fortunately, we will see that we don't need it. Already at the low amplitudes, we're already getting so much damping that we will never get any inline response, as we will see. Right? Now, what do I do to validate these results? Well, I can't, without a time domain VIV model, I can't compare the response for VIV, right? But what I can do is apply a load that is kind of similar to what it sees in VIV, and then compare, on one hand, an incremental time history analysis, and on the other hand, the results you get with this linearization method. And this is here so that's the load. The load is basically like the horizontal load that would be in the first lateral mode. And I apply that, and this then shows you the response you get there. And the response, since you are vibrating and the thing is buckled laterally, it wants to go a bit further out laterally. So there's some static drift in addition to the dynamic response. Now, what I do then is I looked at the last 8 cycles, and from that I get an amplitude, and that amplitude I plot at the next plot, and I do that for a number of different cases. So here's what comes out of the validation exercise. Each of the dots, the circled dots, are a time history analysis, and the lines that you have are what you get from the analytical, basically from the amplitude-dependent mode, which also requires a little bit of numerical calculation, but not much. It's just this. And then and what you can see is they all agree pretty well, except for one. Yeah, one is far off, right? Somebody is far off. And mind you, also note that most of these are pretty low amplitude. The highest amplitude is 0.09 diameters, and that's where it goes far off. So kind of getting to where those modes start interacting and that's where it starts going far off. What happens there with the case that goes far off? Well, this is the response I get for the one far off. And it looks, I apply a harmonic load, but the response is not becoming harmonic. It's still almost chaotic. It's sort of beating and it's doing things. And the amplitude I plotted was based on the last 8 cycles, and actually elsewhere it has a higher amplitude. And on top of that, on top of the inline amplitude, there seems to be a cross-flow amplitude that is coming out of these excitations that's even larger, right? And that is the plot that came out too low when you used the numericals. But if you include all these, if you look at the highest amplitude, it's closer. But I think it does still show that, if you have strong nonlinearity, be careful about linearization. You can't. If the problem is difficult, it's difficult. There's no way around it, right? Now, what's the effect of this on VIV? What I did now is I said, well, let's compare with just the standard method you would analyze. And then I said, well, if you do the standard analysis, you don't rely on much axial restraint at the sleeper, so let's assume 0 axial restraint. Use soil springs like they are recommended in the recommended practice that everybody loves because it tells you exactly what to do. And do the analysis. That gives you this dashed line for the response, inline response. And I'm only focusing inline. There's no cross-flow here. And also no cross-flow in this inline. And it goes up to 0.12 G, and you get a standard thing for inline VIV. But if you put the amplitude-dependent modes in there, what you find is firstly, at very low amplitude, you have this extra restraint, so it has a higher frequency. So you only get onset at the higher velocity. Once you get that onset, the damping is very high, so you never get high amplitude. You're at 0.02 diameters. That's well within the range of the validity. Yeah? And well, it's a big reduction of amplitude. And if you now convert this to fatigue damage, there's not only the amplitude effect, but also the fact that if you use the nonlinearity, there might not be such high stress concentrations. The difference is even larger, about four factors, 4 times 10 to the 4, right? So you go from inline being a critical thing for these, which often it turns out to be when you do the D&V calculations, to inline being no concern anymore for this case. Crossflow is a different matter. Crossflow is much less sensitive to damping and also kind of complicated for the ERP span. So these are the conclusions about the ERP span. I think I've mentioned these already. So what are the general learnings we can do about this linearization method, more generally than beyond the ERP span? What can we learn about this linearization method? Well, when we linearize, we are typically looking at one mode, and we are doing the linearization that's appropriate for one mode. But if we're now going to have a multi-mode response, we can do a linearization for each mode. But the reason we do multi-mode is because we want to superpose. Now, superposing nonlinear things does not work, right? So then it becomes a problem, right? If you have so you tend to get interactions between the modes instead. So if it's really strongly nonlinear, you might have to think about, what other ways. You could get some idea of the effects with this, but it's not going to be necessarily the full answer to the story. Oh wait, I went backwards instead of forwards. Now, what about future R&D priorities related to spans, right? I think more pipe soil, because having had these capabilities to account for pipe soil interaction in a realistic way, we don't have very good pipe soil interaction models yet. And I think some of the work that's done here in TIDE is going to help with that, because we will have then more pipe soil interaction models and to develop it more realistically rather than just a simple frictional model that I've had here. Right? So I think that's very important. And I certainly look forward to the cooperation here too. Now, what happens with the time domain? If you really have strongly nonlinear case, you need the time domain type phenomenological models if you don't want to go to full-blown CFD. And there's been a huge amount of work done on that. A huge amount of work and a lot of validations. Unfortunately, everybody comes up with a better model, right? And so the validation effort has been diluted over many, many different models. So when you look at it more as a user than as a researcher, you say it's overwhelming. Right? You're not quite sure where to go. I think if I were to use it on consulting project, I would pick one, and I would do the validations for cases similar to what I have in my problem, and then I would try to use it and see what comes out with it, if necessary. What else? Here's one, is to reject black boxes. I think that in the industry there is a tendency to sometimes of accepting black boxes. I mean, if you are a project manager and you want to come with answers, people have used this black box all the time, and Shear 7, for instance, right? And there's a huge amount of effort gone in calibrating this black box. And so why don't we use it? Well, you could use several black boxes and get an idea. But the trouble about that is that the industry goes with the black boxes, but what does academics do? And how is the communication between academics and industry coming down? How can the research progress and have impact on practice if people are using black boxes? So I've always been also in the consulting, if you review the work of somebody, say, well, where is enough information to make your results reproducible? That should be also in industry a requirement as well as in papers, right? Even in papers, it's not always. And so I'm quite in favor of that, and always fighting that, but sometimes with a bit of success, sometimes less success. Well, you do what you can. And then I think now about AI, everything is coming with AI. I think it's no longer so much a question of whether to apply AI or how, but more about how to apply AI so it will be effective, right? With so much literature from which you could learn something, you would think, well, maybe we can feed all these literature into an AI model and then ask the AI model the questions we want to know, right? And it could point us to and help us that way. This is perhaps the highest level of using the AI in the sense that it just does everything for you. Yeah? At the much lower level, you could say, well, if I look at VIV amplitude, the response amplitude, it's a function of many variables, right? And we want to estimate a function of many variables. And actually, an artificial neural network is exactly that, a way of estimating a scalar function of many variables, right? And maybe we could use artificial neural networks to fit those data. That's at another level. But so I think there are various people doing work on AI, so I think it has, because also part of the problem is that there's so much research being done in academics that it becomes difficult to kind of absorb it all and apply it all, right? So there becomes a disconnect, and if kind of AI can help bridge that gap, it could be a good thing. Well, thank you very much for your attention. If there are any questions, I'm happy to take them.
Any questions? Do you have the microphone? Hopefully this is still working for people who are online. I don't know if there are any questions in the chat. Yeah. So put questions in the chat if you got me, or from the room.
I understand, Ralf, that you're saying the inline VIV, you are much less concerned about it?
Yes.
Yes, okay.
Yes.
With the cross-flow VIV, as the pipe gets closer to the seabed, the flow characteristics can change significantly.
Yes.
Is this an aspect that you are taking into account?
In principle, no. But there's work that has been done for that, but not so much of, I guess,
I think the cross...
Mariam is doing work on this, in fact, right? And we had a JIP on that not so long ago because we were concerned about the interaction with the near seabed.
Yeah.
And there were some suggestions that if it's near the seabed, it has no response at all, right? And so we had a JIP on that, and there's been a paper published on that. And in this JIP, what we did is that there was limited number of tests that we did, and there's several parameters that influenced the VIV, and we just varied one parameter at a time rather than all the combinations of the parameters, so you just couldn't limit of how many tests you did. And it looks a little bit like that might not have been quite enough to understand all the complexities of the behavior with the interaction of the seabed. Yeah. It's like a lot of the things that you throw in another parameter, you have to multiply that parameter, each value of it, with all the other parameters that you already have to consider, right? And so it becomes quite a lot of work to do all the research that's required to put that in there. Yeah.
Thanks, Mike. And I guess as a teaser, that's exactly in time what Mariam's work is looking at with the apparatus that's now out at the large O-tube to look at that amongst a bunch of other parameters as well. So there'll be more work on that coming. I have a question, Ralf, for you. Just you showed when you did the back analysis of the pluck testing, you showed the softening with increasing amplitude. But just that based purely on back analysis of the pluck testing?
Yes.
Yeah. So I guess it's a relatively small number of cycles in the pluck test. So each pluck is only a few cycles before a very short period of time. So it's
the plot has several tests in the same plot, right?
But spaced.
Yeah, spaced.
Time apart. I guess the RV's got to move over and pull another rope and
Yeah,
do the rest of it. So each one of those was a relatively small number of cycles. So
Yes.
potentially a relatively static response, a pipe saw response. And I guess we would expect if we were to do a lateral test, you would get quite a large nonlinearity in a static response, maybe consistent with what you see there with that softening behavior, but that would be amplitude dependent. So you get a nonlinear lateral response.
Right.
But when you go to VIV, I guess, if it does vibrate, now you're talking large numbers of cycles. So many hundreds of thousands of cycles over its life. So would you expect it to change? Would it? I mean, I would imagine it's going to get, it's going to head towards a steady state and a softened response. How do you translate the work from the pluck, which is closer to static because of the number of cycles, into outcomes for a lifetime with large numbers of cycles?
No, this is what Vasileios is doing. Huh? So yeah, that's certainly a good point. But I mean, even if you reach a steady state response, there can still be an amplitude dependent, though. Amplitude dependence, right?
And I think that's what we do see.
But
it's quite. It may be less, I guess, is what I'm. Maybe more, maybe less, but it may be quite different, I guess, to that semi-static response when it's a small number of cycles.
The properties may be different.
A large difference from a really stiff, small displacement response through to, a sequence stiffness which would drop quite a lot, versus at the end of the large numbers of cycles, maybe the different, the sensitivity may change, I guess.
Yeah, I mean, certainly the if it's a clay type soil, it might be initially the undrained strength, and with many cycles, it becomes the remolded strength, right? For instance, which is quite a different strength. Yeah, I think that's certainly the case. I mean, we can't tell from this test, but maybe from the future we can, right? And then, or if you did, you could think about doing, then you have to be even more courageous. I understand that here in Australia, people don't dare to do plug tests because they're afraid that you'll, do damage to the pipeline. We calculated the stresses and we thought it was okay, but okay.
Needs must, I think.
Yeah.
You needed to do it.
And then you could even think about putting a vibrator on it, and then you could keep it vibrating for longer.
I guess, I mean, we know that some of our tide partners have done that and put sensors on and have measured data. We'd be encouraging others to do the same, but there are some challenges, I guess, even with monitoring how you use that data. One of the key issues we have is, can you trust it? You have data for a short period still. Can you extrapolate out? And DNV has some limitations in its current guidance in regards how you can use outcomes from short-term monitoring periods. That kind of works against the cost associated with acquiring that data.
Right.
Which is a bit of a shame.
Yeah.
Any other questions?
Thank you. So Chris Sanders is asking, are there any considerations around point force loading, like plug test, versus disturbed load testing, like real world?
Well, yes. I mean, if we look here, where was it? Where was the plug test? Now, if you look here, for instance, right, you can see that the point plug test will excite not just the first mode, but also higher modes. If you plug it in the middle, you will only select the symmetric modes and not the anti-symmetric modes. But still, you might have the first mode and the third mode. And here, if you look at this waviness, you have some evidence of higher modes entering here. But this will tend to die out, and also the way I've processed this, it's filtered out because I'm kind of looking for fitting the mode 1 only, and if it's a higher frequency, the errors will cancel one way and another. They won't pull the estimate one way or another. So I think that the higher modes in this case probably die out fairly quickly, although you plug it only one place, it still gives you a reason, especially if you have clearly one dominant mode. We did all kinds of plug tests. and some of them with mini spans and different things. And some of the plug tests actually were quite strange. They seem to have I could not interpret them in terms of modal properties. And what I suspect happens is that there might be, you install a support on a pipe, and then with an operating cycle, it pushes the support down a bit, and then the pipeline maybe just gets a bit cool, it just comes a bit above, and there's a tiny little gap, and that gap, even at very low amplitude, is slamming. And then it will throw off all your interpretation in terms of modal analysis and things, mode fitting and so on. And those things could be happening in some of these things. So, yes.
Might be a challenge.
You could do more with those data. Huh? You could do more with those data, and I guess we tried to get them, but it was too complicated.
Well, I wonder. We've been doing plug testing in the centrifuge on piles recently, so vibrating this way. I wonder whether we could use the same device and actually pluck on a span. As well. So maybe,
that'd be interesting.
Maybe a future challenge, Giuliano.
Yeah, I mean, really, you don't have to. The distress to the pipeline is not much, huh?
But it could be quite interesting to. We have our SCR model for pipes and free spans. Potentially combine that with the pluck apparatus and actually simulate some of this. Would be quite an interesting exercise to do.
Yeah. And even if you do it on a full-scale pipeline, I mean, you can calculate the stresses due to your plug test and compare them to normal stresses due to operating cycles, and then assess whether how big your risk is,
Okay, so I think he's Gary Cumming. That's right. Sorry. So Gary is asking if the time-dependent model indicates that it takes tens of seconds for response to build or stabilize in a steady current, what implication does this have on VIV response generated by a store?
Okay, so this is the question of unsteady flow. Huh? Like you don't have steady flow, what is the response?
And if it's constantly changing,
and
forward.
Yeah, and this is something that is, well, it's the guidelines we have from DNV do consider this, right? And that they modified these response functions according to the Coulomb-Carpenter number of this response. But if Coulomb-Carpenter tells you basically, when you have a wave response, it goes up and down, and the movement of a particle, and it's basically the number of pipe diameters that it moves up and down, multiplied by a constant pi squared or something. I don't know what the constant is, but there is a constant there that I don't remember it, right? So just and if it's Coulomb-Carpenter is very large, then at least for some time it's seeing kind of steady current likes, right? And for those cases, there are no corrections made. Now, to account for that, the time domain VIV models that are based, they would automatically be able to account for this, right? But the frequency domain ones, and here in the response functions, they used highly empirical things, and I'm not sure how good they are. I'm not sure how good they are. I think they're probably conservative, but how accurate they are, they certainly have jumps in the response function that they give, the empirical. It's discontinuous function, but that's probably reflective of how much confidence you had in those predictions, right? So yes, that's certainly an issue.
Okay. Last questions. Otherwise, I think we've used up our hour.
Yeah.
So I think we'll just get everyone to join me in thanking Ralf for another interesting talk. It is being recorded, and we'll make it available online. So for those from industry who want to share that around, or think that may have colleagues that would be interested but were unable to join today, it will be made available online, and people can grab a copy later. But otherwise, thank you, Ralf, for another talk, and thanks for your time here.
Yeah, thank you.